Hello everyone and welcome to my presentation. I'm Sebastien and you might have seen me before in PasswordsCon presentations, notably around the Wikipedia word list, which I still intend to improve with AI technology at some point. I'm just learning little by little because it's not my field. And particularly neural networks, as I was presenting here at the University of Cambridge, to isolate words that are not made just of letters, but something like .45S $W, as in the 45 Smith & Wesson caliber, if someone were to use that as part of their password or passphrase. So I'm learning about all those new neural network technologies, but I got an even better one just recently called Zoe, who is awesome, and she's now my #1 priority. I work for a great company called Digital 14, where we take security as seriously as possible, going to the extent of, for example, melting the case of chips, the packaging of chips, decapping the surface, adding all sorts of probe, poking at them with lasers, messing with the power, all sorts of electromagnetic attacks, and that's just the hardware lab, actually, as part of Zenith Labs. So we try to evaluate security products from all possible angles to see if they are any secure at all or what level of security they provide. And, for example, if you have a hardware security module which is supposed to keep AES key in hardware, for example, and making it impossible for someone to extract it, well, we would mess with its power, see how it reacts, things like that, and analyze the signals. So that would be my team, for example, and be able sometimes to extract the encryption key, which is not supposed to be possible with the HSM hardware security module. So being lucky to work in that sort of environment, I also participate in client-server designs in the ideal world, basically. So we do everything from supply chain risk management, where we can even kind of force factories to improve their security, to not make it so easy to put backdoors in equipment from the factory. Hardware assurance, so that's putting equipment that you receive under X-ray machine, for example, looking for any suspicious addition of a chip, like you might have heard of with the Supermicro stories and things like that, or just counterfeit chips, which happens quite often, actually. Software assurance, which is kind of like code review, but taken to the extreme. So you probably heard sometimes that governments are asking Microsoft to show them the source of Windows, and then Microsoft welcomes them to Redmond to look at the source of Windows on their own computers there, I mean the Microsoft computers, which is kind of proving nothing then, because you don't know if you're looking at the real thing. So that's all the considerations of software assurance. Then once you have all of this satisfactory, so that you are expecting at least something usable out of what you have received, you then would start with local attestation, which is all of the technologies like secure boot, trusted boot, taking it to the extreme with things like Linux integrity measurement architecture, and maybe some newer ones like Intel Software Guard extensions or something like that. I haven't looked into that one, but Linux IMA is already very good. Mutual authentication, so that's nothing new actually, but it seems to be more in fashion now. It's basically not having only server certificates, but also client certificates, so that clients and servers can mutually authenticate each other. And now that you have the previous two, then you can even do something called remote attestation, which is, for example, asking the Trusted Platform Module, TPM, which is kind of like a third-party observer on the other side. So you're connecting to a remote computer, and you want to make sure that it's running actually what you think it is running. So that's how you can do that with the remote attestation. You can ask the TPM on the other side to provide you a digital signature of the state of the machine on the other side. But in the real world, actually, I have much admiration for the rest of the security industry, who has to deal with characters like Dave here in this comic, who would choose a password like Dave is the best, change the letter E to the number 3, change the letter I to an exclamation mark, and that looks like a very strong password, so let's use it everywhere. Also, even me personally, just by lack of space, for example, I cannot put a server room in my flat or something like that. I might do my hobby projects with a Raspberry Pi, but here it's just a symbolism that most or many projects, even from a small company or something like that, would be running on a VPS, like a virtual machine that you're renting for cheap from some cloud provider. So the idea here is basically that it doesn't have much power. Then, especially if you're running it from home, you would hide it behind a service like Cloudflare, which is exposing their IP address instead of yours to the internet. And as much as I really like Cloudflare and believe that they take security seriously, you have to keep in mind that in most of the cases, actually, they are decrypting and re-encrypting the traffic. So when someone is visiting your website, even if it's called https:// it's HTTPS only up to Cloudflare where it's decrypted, and then there might be another HTTPS connection to your home or even a clear text one, depending on how you set it up. It's possible, of course, to have it all the way, but that's, as far as I checked, reserved for enterprise clients of Cloudflare. And again, it's just an example, so I'm not blaming Cloudflare here, and it can be the same idea with some other cloud providers. And it's not so much of a risk here, but you hear every once in a while of some companies, even Facebook, I think it was a couple of years ago, where some developer or some admin mistakenly enabled some debug logs, and everyone's passwords were being written into logs. So that's what might happen here. So we have to keep in mind that then your visitors' passwords might be written to some logs here unintentionally. So it would be better to have really some sort of end-to-end encryption. Another thing that you see quite often is for corporate visitors. So someone who might visit your project from their work setup. So they have like a work laptop, which in itself nowadays is fairly powerful, actually. What happens is that they are usually or quite commonly put behind some sort of web security appliance, which is actually doing even worse, is actually doing a man-in-the-middle attack against that HTTPS traffic, but cooperatively with the permission of IT. The problem being, however, that it's so easy to hack so many company networks. If you've done some pen testing, you know how easy it can be most of the time, really to the point of getting boring. So when those company networks are so easy to hack, then it's not a question anymore of just being able to for the attacker to access all the company intellectual property, but then the attackers are even able to access people's bank accounts or whatever private information that people might be accessing from their work laptop during the lunch break, for example, because of this very dangerous practice. Then visitors from home might visit your website with a gaming PC, for example, which is vastly more powerful than your Raspberry Pi or the VPS. And just in general, you have all sorts of visitors on the go with flagship phones also, which are very, very powerful nowadays. So to put all of this into perspective, let's talk about different categories of hardware. So the absolute unit of performance is the ASIC, the application-specific integrated circuit. So it's basically you take an algorithm and you hardwire it. You put atoms on a printed circuit board. I mean, you make the PCB out of it. And this circuit board is capable of doing only this algorithm and nothing else. However, it's the absolute fastest at doing it. So it's kind of like this land speed record-breaking car that doesn't even look like a car anymore. It's not really possible to call it a car. It cannot even take turns or whatever. It's the absolute fastest, but definitely not practical. So in general, you would have something more commonly called the FPGA, a field programmable gate array, which is not yet a chip in the sense that you might think. It's more like a virtualization of the previous one. So you still have to design this printed circuit board, but instead of manufacturing it, it's virtualized within this FPGA machine. And so it's kind of like a Formula One that already is much more practical because you can do more things with it. You can take turns in terms of driving, but you can also replace all the time in your FPGA. You can put different algorithms. So typically in pen testing, for example, you might use this sort of hardware from CyEngines, and you don't want to be able to crack only one sort of algorithms depending on the pen test. You know that depending on the target, it's different sorts of algorithms. So it's very useful to be able to just swap them in and out of your hardware. And this is still very, very fast. It's not as fast as the ASIC, but still very fast, much faster than GPUs, for example. Or it depends, but in many cases it's much faster. So in general, then you would have your everyday computer that if you want to have the maximum performance out of, you would program in assembly or C, for example, to get as close to the hardware as possible. And it's much slower already. It's kind of like this everyday car that you can take to the supermarket, you can take to work and so on, but it's all of that at the cost of performance. So it's great in terms of versatility, but it's already far slower than the previous two. And now you have GPUs, so graphical processing units, which is like the main part of a graphics card, as you can see on the left, typically now in gaming computers, and usually the most expensive part of a computer nowadays, or at least like a gaming one. And it's actually slower than a CPU by itself, but it's more like a freight train. So the freight train is probably slower than a car, but it's pulling so many carriages behind it that it's more powerful than a car in terms of delivering goods to a particular destination. So it's the same with the GPU, where as long as it's doing everything exactly the same, then it's faster than a CPU. So just to give you a rough example, it's not comparable like apples to apples, but just roughly, you can see that in a GPU there are nowadays 4,000 cores. So it means that you can just in one go try 4 different possible passwords to see if one of them cracks the target hash that you are trying to crack, as opposed to even the most expensive CPU nowadays has like 32 or 64 cores. So a CPU is nothing in terms of password cracking compared to a GPU. Then going deeper into, or higher into levels of abstraction, and apologies, apparently that slide disappeared from the internet, but it was a good example about Java, which popularized this idea of bytecode, which is kind of like emulating an imaginary chip that doesn't exist. So if you look at the leftmost bar in that bar chart, that was going to be the performance of the Pico Java chip that they were considering making at some point as a real-world chip. But in the end, it wasn't worth really commercially, so it didn't really happen. But compared to the other bars on the chart, you can see that the rest of the computers, so PCs at the time with Pentium chips, or nowadays your phone, even though it has a little bit of Java acceleration, it's already much slower than if it was running real code, as in native code. So it's kind of like this golf cart in the sense that it's a car, but it's not really in its environment, so it's not very fast. And then finally, there is scripting, as in JavaScript, for example, is probably the most common language, maybe even more than spoken languages nowadays. And it's great in the sense of everyone can do it. So it's like this toy car, everyone can drive it, and you can still do really cool things with it, like this toy car is in a McLaren. But in terms of performance, you see it's far, far slower than everything else. So just in terms of very rough order of magnitudes, because it's, again, not an apple-to-apple comparison, because even with performance per watt or performance per dollar, things, etc., it all depends on what chips you choose, what sort of hardware architecture, what sort of attackers you have in mind, like teenage hackers or nation-state actors or whatever. But just very roughly speaking, you would have the defenders using technologies on the left, not having a fighting chance against the attackers with the technologies on the right. And this is perfectly demonstrated with the evolution of Bitcoin mining, which is very much like password cracking, actually. So the idea is like you have bank transactions happening like a statement every 10 minutes, let's say, for example, and the miner is able to add one more transaction to rewrite itself if it finds a particular value, like cracking a password, which produces a hash that is lower, starting with a certain number of zeros. So it's essentially password cracking. And it is really based on SHA-256. Bitcoin is mainly on SHA-256. So in the beginning, people were mining Bitcoin on CPU, but then someone quickly thought, oh, well, let's do it with a GPU. So everyone moved to GPU. Then at some point, it made sense to put the money and time into designing FPGA designs to do that. Like I said, it's not really a kind of programmation. It's more like designing circuitry. So it's already much more involved than GPU programming. And nowadays, actually, all of that even is kind of worthless compared to ASIC mining with ASIC mining of Bitcoin, because Bitcoin now is so valuable that it just made enough sense to manufacture specialized chips just to mine Bitcoin. And this is just because Bitcoin, being based on SHA-256, didn't have any sort of breaks, any sort of protection from this evolution to faster and faster hardware. So one of the things that can be used to prevent this going forward is called the memory hard function. So the idea is that you want to see what is the difference between the left and the right. On the left, you actually have quite a bit of RAM at your disposal. And on the right side, even though GPUs nowadays, for example, have like 16 gigabytes of RAM and so on, that RAM is actually tiered in slower and slower, or relatively slower and slower speeds, down to when you want to do the actually fast implementations of algorithm, you're more thinking about in terms of 64 kilobytes of RAM. So memory hard function is a function that requires more than that. For example, it ideally even requires gigabytes of RAM. So that makes it really annoying for the GPU attacker, because they cannot use this really fast RAM. They have to use this lowest tier RAM, which is the bulk RAM, let's say those 16 gigabytes that you have in your GPU. But it's really already slowing down the GPU a lot more than actually the CPU that has this all of this RAM at its disposal normally. So this was exemplified, for example, by the Ethereum cryptocurrency, which is based on the Scrypt, probably the very first, I think, as far as I know, the very first memory hard function by Colin Percival. Actually, he presented it at PasswordsCon in 2012. And it was great at keeping Ethereum kind of stuck to GPU mining and making it very hard to implement with FPGA and ASIC. But as you can see, with the recent announcements, there are factories that are now going to launch ASIC mining for Ethereum. So it means that it's not a complete solution. It slowed down this evolution. It didn't happen as fast as it did with Bitcoin, but it's still doing exactly the same. So what else can we do to avoid having the attackers in terms of password cracking getting the advantage over the defenders who have to use the slower technologies on the left? So another new field of research is called bandwidth hard functions. And it's not bandwidth as in your internet bandwidth. It's more bandwidth in terms of local cache versus far fetching from the RAM and so on. So it's the internal bandwidth of systems on chips and so on. But just in general, the idea to make this kind of a fair fight between the defenders and the attackers is to go for the Achilles heel of the attacker. So what are the specifics of all these hardware architectures on the right that would make it much harder for attackers to try to crack your password in a way that is kind of easy for you but hard for the attacker? So for example, like I said, with the GPU, there's a typical pattern that you have to follow called single instruction multiple threads, meaning that all your threads have to be doing exactly the same thing. So that's great for password cracking if, let's say, for example, you're cracking some MD5 or whatever, and you put 4,000 different candidates of guesses like AAA, AAB, AAC, and so on. You launch all of them at the same time, and for that, a GPU is great because those 4,000 threads will be executing exactly the same MD5 at the same time, and then maybe one of them has cracked the password. But we don't want that as a defender. We don't want the attacker to be able to do that. So maybe we can design the algorithm in such a way that it's forcing something, it's blocking the possibility of using single instruction multiple threads. Maybe we can make the execution dependent on the password, for example, which I'll get to later. To defend against FPGA, like I said, the idea is FPGA is kind of virtualizing electronic circuit boards. So it means that it can only contain a finite amount of them. So if it's virtualizing tiny chips with very simple algorithms like AES, MD5, SHA-1, SHA-2, whatever, FPGA machine can virtualize many of those chips. So what you want here is kind of counterintuitive in terms of crypto. You actually want a complex algorithm so that the chip size is actually big, and then the attacker with the FPGA doesn't have enough room to run many of them at the same time within one FPGA machine. And finally, how to attack an ASIC? Well, it's simple, basically. It's difficult to manage in terms of maintenance and so on. But you just have to make your algorithm not fixed, so that if there is a risk that tomorrow your algorithm will change, it means that whoever manufactured specialized chip today to try to crack your algorithm. Tomorrow they can throw this to the garbage because you changed it tomorrow, and then they cannot change it because it's all set in stone with their ASICs. And finally, perhaps the current state of the art is actually the random X algorithm that was just added to the Monero cryptocurrency a couple of years ago. Around 2019, they already had 4 different security audits of it. And it's basically trying to do all of that, like going for the Achilles heel of these various technologies. And so far it seems to be holding indeed, because Monero is kind of stuck on the CPU mining. And of course, well, there's a bit of JavaScript and WebAssembly mining happening also, because it's being used by malicious people hijacking your computer. If you're visiting their website, they might be mining Monero in the background of your browser, for example. But that's unrelated to the technology itself. So to recap, basically, we have all these clients that have quite a bit of untapped power, and you have your little server, which might be a Raspberry Pi, a VPS, or whatever, which is completely outnumbered and having to do so much work. So what can we do about that? So let me get some water, actually. So if you read XKCD, you probably know this common example of a password or even a recommendation. It's often used in password cracking research and so on. But I have issue with this one because my hands even get distracted by the horse and I write stable instead. But what if you're unstable and you go horse, bears, beats, Battlestar Galactica? What if you actually are listening to Metallica when you're typing your password? You might be typing this instead. What if you're listening to even more distracting music like the Beach Boys or Aqua? What if you're descending into madness and mathematics? So let's just use a correct horse banana for scale and conclude that actually we need to truncate at 14 characters. So now, well, we forgot kind of where did we put all those caps, so it's difficult, and especially some people have the caps lock key instead of shift, let's try to help everyone and just to be sure capitalize all of this. So we end up with correct horse bar, all uppercase. That's still a lot to remember. So what can we do about this? Can we do like in the movies? I would really like to see that in the real world, where we can crack password letter by letter. But that I have never seen happen in real life because that's not how passwords work. But maybe we don't have to go as far because it looks like it's 50% correct. So let's just divide it in half with this a fancy software engineering pattern called divide and conquer. Just cut it in half, and now we realize that each half is 56 bits, which is perfect for this DS algorithm from the 70s, so it must be pretty good by now. But what can we encrypt with that? Because blockchaining sounds hard, block padding sounds hard, and well, let's just encrypt a string constant measuring exactly 1 block. So you would take this original password, have truncated it to 14 characters, uppercased it all, divided it into 2 halves completely unrelated, and encrypted DS with correct as a key of KGS something something, and separately DS with horsebar as a key of KGS something something. And now if you're wondering, like, why am I telling you all this? Who in their right mind would design and use such a ridiculous algorithm? Well, you might be surprised. So if you think that it's a thing of the past, well, actually an article even from just last month is saying that there's still so many people using Windows XP, and it's not just people at home. Like you have the National Health Service in the UK, which is managing all the hospitals. It's a big deal in the UK. It's getting hacked all the time because it's still running Windows XP and all sorts of issues like that. But then you might think that, well, it's only an issue with organizations that don't really have an IT budget, maybe. But as you can see, there's a £3 billion aircraft carrier being delivered 2 years from now, which is apparently getting Windows XP with it. So some numbers, just to have fun here. So a long time ago, like 14 years ago, I was pen testing a defense company. So keep that in mind, that a defense company. So it means that you're not far from making security issues a matter of life and death. I was there pen testing them with Jean-Michel Picot, whom you might remember from the DPA PIC. So a tool that is extracting secrets from Windows Data Protection API. He presented that at Black Hat Federal 2010. And so we were just getting ready there. So I think by that time I was still looking for electricity socket to plug my laptop charger or whatever. And because it was kind of a big deal, there was the CSO, the CEO, and various members of the board of executives who were watching us getting set up. And the CSO was telling the CEO, don't worry, there's no way they will find anything because the admin password is all random, all uppercase, lowercase, special characters, whatever. And as he was saying that, Jean-Michel asked him, excuse me, sorry to interrupt, is it 3 capital D, lowercase s, and so on and so on? And it was really that. And it was not even like 2 minutes within our pen test of a defense company, just because Windows is so bad at protecting passwords. So nowadays, there's not even a need to have rainbow tables anymore, because as an attacker or pen tester, you would have at least GPUs or maybe even FPGAs at your disposal. And because they are so fast, there's just no need to use perfectly good storage space for rainbow tables, because you can do it just as fast by cracking the password from scratch every single time. And just to give you an example of how bad this is still nowadays, especially now that computers are faster and faster, it means that even just a teenager with a gaming PC from this year, so not someone like who is an evil hacker with advanced hardware like in the movies or whatever, just a regular teenager with a gaming PC would crack your password in 15 minutes. So he would be admin of the aircraft carrier or something. So what can we do about that? Well, apparently DS is pretty bad, it's getting cracked left and right and so on. So what can we do about that? Well, FIPS 46.3 says to replace DAS with triple DES, but actually triple DES was designed, or at least in the encrypt construct, to be backwards compatible with legacy systems that only understand DES. So if you do triple DES with 3/3 of a key that are the same, so like DS 3 times with the same key, so it means that you just fall back onto DES. You're doing DES encryption once with a key, then decrypting it with the same key, which just cancels itself out, and then finally encrypting once with DES, so now you're just back to square one. So, well, now we have to completely change that design that that ridiculous algorithm that I presented before. So how can we use triple DES actually with the whole password? Well, we would need 168 bits for a key for the triple DES. And that means at least 21 characters, not taking into consideration the entropy, the fact that one character is not at all one of 255 or 56 possible combinations. So what about something small, requiring a smaller key like AES 128? Well, still you would need at least 16 characters as a password, which is definitely not something very common. So what if you take this example from Microsoft documentation that actually IT administrators use in the real world, so password with the @ instead of A and 0 instead of O, and just space it out, putting some null character, kind of like a space in between every single one of those letters. So it kind of looks like now you have 16 letters. So is it good enough for 128 bits of passwords? Or what about the shorter passwords? I didn't talk about that in the previous slides and so far. So, well, what do you do with people who have only like 10 letters or 5 letters or whatever password? So you would still pad it with zeros, which means that the rest of the key is kind of worthless. So all of this, well, sounds very hard actually. You have to worry about entropy, key derivation functions, and so on. So let's just use MD4, you know, like from the early 90s, 1992, if I remember correctly, of the Unicode 16 little endian representation of a password. And again, if you're thinking, why am I telling you all this ridiculous algorithm? Well, that's how Windows is trying to protect your passwords nowadays. So I'm bashing on Windows, but I have to respect that Microsoft is trying to offer this backwards compatibility, which is great in terms of IT, but from what I see from a lot of personal experience, apparently many security teams, maybe most of them, if not all of them, have no idea that actually the main defense of their whole infrastructure is like a rusty old lock from the 70s or the early 90s at best. So just a quick idea of numbers. That's something that Jeremy Gosney presented at PasswordsCon, Passwords 2012. Well, he was able to crack all those passwords, Windows passwords at the time in less than 6 hours. So you might say, well, to be fair, actually, that article is about fully random, but only 8-character passwords. And yeah, nowadays, thankfully, people are being asked to use longer and longer passwords, rather a passphrase instead. And so maybe in your network, you think that it's not applicable anymore. But actually, have you checked the passwords from IT? Because the rules don't apply to them, and they put passwords that do not expire. So it's very common, even just like 5 years ago, I was doing a pen test where, thanks to Mimikatz, that's another reason to not trust Windows security at all, I dumped around 800 passwords of a whole multinational company and was admin on 5 different Active Directory domains in just 1 week because of all of that weakness. And the administration passwords were 9 characters long and all lowercase and maybe a couple of digits. So, well, what can we do about all that? Obviously, MD4 is too weak, so let's use MD5 because 5 is bigger than 4, so probably it's better. And let's use it twice to at least be twice as better than Windows. And why? Well, for real this time, it's also something that I've seen happen before where you might have this service provided to many customers. Like in this particular case, it was a large corporate email service with tens, maybe hundreds of thousands of clients around the world, or visitors at least. And it turned out that all those usernames and passwords were only protected with a single round of MD5. So it's already much better than Windows, but it also is very bad. So what should we do about that? How can we actually properly secure this? Well, should we consider Argon 2 the new best practice from 2015? No, maybe it's too recent. So scrypt from 2009, not too recent. Maybe bcrypt from 1999, not too complicated. At least PBKDF2, which everyone has heard about, I guess. But no, apparently still complicated. So we'll just do something that is as compatible as possible for some reason that doesn't achieve anything in terms of improving the security, and waste a lot of time and money just to migrate everyone by forcing them to change their password to a single round of SHA-256. So if you remember those previous slides that I was showing earlier about rough orders of magnitude, SHA-256 can be cracked at hundreds of trillions of guesses per second. So it's hundreds of millions per second. So it's completely a waste of time. And how does that look like in the real world, where you have these companies that say, well, we take security extremely seriously, but then they get hacked by a teenager. So that's exactly why. So how to actually take security seriously? That's a presentation from Alec Muffet, for example, at PasswordsCon 2014, where he was explaining how does Facebook do it. So it's basically a question of doing layers. So let's say you just started a service and you don't really know anything about security, or maybe you don't have time to worry about the username database security yet, so maybe you just store everything in clear text. It's not very good, but maybe next week you'll get around to improving it, and then you heard somewhere that at least MD5 is better than clear text of password. But then at some point you realize that all the users that have the very same password have the same MD5 hash. So that doesn't look like a good idea either. That's still a problem with Windows nowadays, but they're not fixing it. So at least you are doing something better than Windows. You put a salt, which makes the hash for people who have the same password, at least the resulting hash would be different. Then you learn more about password security and so on, and you read about something called a pepper. So it's kind of like a salt, except it's not specific to the user, and it doesn't even go in the database. So what I highlighted in yellow is what you would have in the database itself, whereas the pepper is kind of like a secret that you keep separately from the database. You would keep it in the source code of the website, like the PHP or whatever you write your website with. And that way, what happens a lot of the time is that hackers are able to extract the whole database behind your website, but they are not necessarily able to get to the source code. So in this case, the attack would be thwarted because they don't know what is the pepper. So then you learn about PBKDF2, which is kind of a kludge, like duct taping some fast hash like all of these before together, but to try to at least slow it down a bit. And as the time passes, you might add layers and layers just to make it harder and harder, because you have to basically find the happy medium of how slow you want to make it for your little Raspberry Pi VPS or whatever your service is running on. But at the same time, you want to find the happy medium with slowing down the attackers. And hardware becomes faster and faster every day or every 6 months and so on. So at some point, finally, you read that, well, it's kind of bad to use all of these hashes, fast hashes that are great for hashing files, like MD5, SHA-2, and so on, but they have no place in being used for password protection. You want actually a function, an algorithm, that has been designed for that. So that's what bcrypt was in the 1990s, for example. So don't worry about the anachronism with the SHA-3 being more recent. That's just examples. But yeah, you are learning about the password security. So at some point you add a layer of bcrypt, and you still haven't required anyone to change their password, just to show that it's possible to do without annoying anyone. Then again, time passes, you add more, and at some point you learn about these memory hard functions to try to thwart the attackers with at least a GPU or maybe FPGA, ASIC, and so on. So you use script as an additional layer. Maybe at some point you add another layer of script. And finally, it's 2015 or more recent, and you learn about this new best practice, Argon 2, and you add a layer each time with its different salt, pepper, and different factors, so that, for example, maybe the first time you added a layer that takes just 10 milliseconds of execution, but the next time you want to make it even like 100 milliseconds of execution or something like that. So that's how you can improve layer by layer, progressively being kind of future-proofing your password security. And at the same time, you might think, especially as a cryptographer, if you're familiar with crypto, you would get kind of a bad feeling for dragging all of this retrocompatibility behind all of this, especially if it was started with a password in clear text or going as far back as MD5, SHA-1, and so on. But you don't really have to, because at some point, finally, users might change their password, or you might get a new user that just arrived when you're already within that generation 9 of your improvements. So maybe at the time you take the brand new password, maybe the word password again, you put it through script, and then 1 year later you add this layer of Argon 2, then another year later, another layer of Argon 2, and so on. So as you can see, you can implement it within your database like that, for example, where this new recent user doesn't have any of the salts, for example, for the older algorithms. So if you remember this slide, you see that, well, there's so much performance on the right, still maybe not as much as a real like nation-state actor, but it's really a pity to not be making any use of this amount of performance that is vastly outnumbering your Raspberry Pi or VPS on the left. So I started building something called HashMore, just because I like to tune security to 11, basically. So it's time for clients to start doing their part. Let's see how we can do that. So let's say, for example, we have a constant C1, just a welcome message. Then a constant C2 that is supposed to be a number used once, but maybe you're not very good at math, or you like to read XKCD when they were laughing at a mistake made by Debian 10 years ago or something. Well, you can use the number 4 here instead of a random number, just as a joke, because maybe it was taken from one fair dice roll. But actually, I unintentionally found a remote exploit with this way, trying to put a large number here, but it better be a small number, actually. So the constant C3 can be the word post, for example, then C4, a well-known unified resource indicator. Maybe if you use Let's Encrypt, for example, you're familiar with that sort of thing. It's just a path that starts with .well-known and so on. And just to make sure that all of that is constant, then you can apply this formula, and you can see that actually all of it is constant, even that MD5 on the right side, all of that can be pre-calculated. So in the end, it's just MD5 of basically the username and password with another MD5 of that again. So MD5 twice, like I was saying. And RSC 2069 is something that actually all the browsers support. It's called HTTP Digest Authentication. It's not commonly used. It may be fallen behind the times or something, but it's still being offered nowadays, so that you can have even a text mode browser. For example, maybe if you're connected to a server with SSH, you might be using links sometimes to quickly access a website. So it's not even capable of displaying images, but it does support this RFC. You can even connect to this website, log in using this method with the NCSA Mosaic web browser that is 3 decades old, or Netscape Navigator from back in the day, or even nowadays people who might be using the no script exemption to disable JavaScript from their web browsing. So basically how to do that, you just make a page that has a link to the login page that by default is pointing to the HTTP digest authentication. And if that's where they are taken, that's the end. They just log in with this password prompt, and at least their password is transmitted with MD5. So we are already doing better with regards to where is about Cloudflare and corporate SSL money in the middle machines. But if the browser is running JavaScript, then you can have JavaScript overwriting this link so that it's pointing to a web form. So that's what you see nowadays. It's just a nice rounded corners box where you put username, password, and so on. But here you have to emulate the same step that might have happened differently with different browsers. You need to emulate this RFC 2069 formula of MD5 or basically username and password, which you can do with a JavaScript library called from Pages Home, which is compatible with browsers even from the early 2000s. And if that browser is so old really that at this point it's already quite a bit of time that has passed, then you can submit this result already, because you know that, well, if you are going to take several seconds, for example, to submit the login page, people might get worried that did they click the button, or is the website not responsive, or whatever. So at every step you are checking, is it half a second or 1 second already? If it is, because it's a very old machine, very slow JavaScript or something, then you can already submit here and the server will take charge of the rest. So now after that, I'm showing as an exercise basically to show how we can start with one of the oldest technologies, MD5, and make it secure in the end. Is it time already for the accelerated crypto? Well, there's something great with all the web browsers nowadays, except Internet Explorer being annoying as always, called the subtle crypto. So if we want to support Internet Explorer users, we have to do a bit of JavaScript instead. Not too much, to not waste too much time, but basically, what if we simply loop SHA-256 until the deadline or until the target, if by luck it's actually fast enough? Well, we cannot do that just like that, because there's a risk of it eating its own tail if it lands on a particular value. Like there's a kind of collisions that then go in a loop. That's why PBKDF2 was invented as a construct, which is kind of duct taping this together, but at least a little bit safely. But it also makes it hard to measure an exact amount of time of this. So you cannot say, I want to do this for half a second. You have to try like for 1,000 iterations and then see how long has it been. Let's try a bit more and a bit more, etc. And it doesn't accumulate because each time it's doing its own thing. So it's not easy to just extend. And you have to be careful also. There's a pitfall with PBKDF2 and HMAC within it, that if the input is longer than the size of the hash, then it will silently pre-hash it, which actually introduces some other weaknesses, some collisions and so on. But actually, if we use my silly idea of starting with MD5, it's not a problem. So to recap, basically we have, let's say, something starting where all the server is doing all of the hard work. And because I don't, it's just simpler to get it done with now. We could also, if the client is capable of JavaScript, WebAssembly, or the Web Crypto API, we can use asymmetric encryption to submit whatever the result was at any particular time. So at any particular step, if it was MD5 or PBKDF2 or whatever. So if you were able to do it, that's great. Otherwise, the server would take charge of it, like I said. Maybe then, if it's a browser capable of JavaScript, it does this bit of PBKDF2. And then, ideally, if it's capable of that Web Crypto API, also called Crypto Subtle, well, it should be able to do this bit of serious crypto, except Argon 2 is not yet supported in it. So If you would really like to see that being supported, hopefully soon, please go there and like this page or whatever, add your support so that it gets added into the standard. So what can we do for now until then? We can use great implementation that someone did of Argon 2 in the browser, trying to go as fast as possible, not doing just JavaScript, but using WebAssembly, which is already 2 or 3 times faster than JavaScript, and going even further than that, a bit faster using this SIMD extension, so like single instruction, multiple data, not to be confused with the SIMT of GPUs. But as you can see, roughly it's still 10 times slower than native code execution. So that means like what we would like to be running directly on the CPU of the visitor. So it still may be a waste of time. So what should we do here? Can we design our own algorithm? And I'm sorry, I really need water. So usually designing your own crypto is a big no-no, but Jean-Philippe Aumasson, the organizer of the original password hashing competition, said that it's okay, and even Rob Graham, for example, it's a great way to learn things. So let's see, can we learn something about this? So I would like to introduce my own algorithm called somewhat memory hard function, but probably cryptographers will call it shaking my head frustratedly. And in the end, at least, hopefully we can just agree that it was Sebastien merely having fun. So what if we start with PBKDF2? Well, it's not a good start because it's basically a speed competition between that land speed record car and your toy car. So not a good idea. Can we get more data out of PBKDF2, kind of like those memory hard functions? Well, PBKDF2 can give you more data. You can say, give me like 1000 bytes or whatever, but actually it's giving you many times the same thing, completely separate. So it's even more of a waste of time. What we want is another construct, which is supported by the Web Crypto API actually, called HKDF. That's great, where it's giving you one hash followed by another hash of this hash. Basically, it's a little bit more complicated, but keeping it simple, it's hashing more and more of the same so that you have this long chain forming. And another thing that you can see with the difference between cryptographers and maybe real-world attackers is that there's a really annoying property in the HKDF that is starting to count from 1 and using a single byte for this counter. So it means that it's capable of giving you only up to 255 hashes instead of 256, which would have been perfect in terms of high performance computing. 4 kilobytes is the size of a memory page, of a page of RAM. So it's like if you want to go as fast as possible, you want your data to fit within blocks of 4 kilobytes. But with HKDF, it's not possible. So you might think, well, can we use PBKDF2 on the left side to kind of combine those together and add this missing hash each time? So you can kind of do it, and you can have all this yellow part that is kind of chaining still itself together when you're using the salt of the last value as the salt for the previous one, and each for the first yellow block of the yellow part, and then using the PBKDF2 value on the left as the key. So it's fairly arguably strong in terms of deriving data, but actually it's not very good because we have this, like I said at the beginning, that PBKDF2 is giving hashes that are completely independent from each other. So it's kind of what is symbolized here with the cyan and magenta cells. So what can we actually achieve? So if we run HKDF, like I was saying, and we want to run it really a lot, like to produce megabytes, if not gigabytes of data. So here I put only about 50 hashes, just to have an idea, because otherwise more wouldn't fit on the screen. And if you imagine that the red part is the amount of data that the attacker can keep in mind by using this more limited memory architectures like GPU, FPGA, ASIC, and so on, then you might think, well, simply I can just spread all of that data and then jump back in times to force the attacker to recalculate all those hashes from the beginning. Then maybe I do a jump forward, in which case the attacker actually is a bit luckier, doesn't have to go from the beginning, can just start from where it was and get to that position each time. So it looks like you are making it easy for yourself and hard for the attacker. Because roughly speaking, there's a 1 in 2 chance that the attacker has to go from the beginning or from wherever it was. So you would think that each time, roughly on average, the attacker has to recalculate half of the memory that you're using each time. But unfortunately, the attacker is clever and can optimize. So they can spread out also their memory as a sort of save point, for example, to just have to go from the nearest save point to wherever you jumped, and then your algorithm is kind of defeated. So how can we make it one way, both ways? Not really. Can we modify the data each time we land somewhere? That would be good, but in the end, probably we want to have modified everything. So let's see at how is it being done in a proper existing memory hard functions like script. So script starts actually with PBKDF2 just to have a lot of data to play with and doesn't care that it's completely independent from each other, because then they are doing the hashing one by one. So they take, for example, the very last hash and input it with some counter value basically into this bright green arrow, which is symbolizing a new hash, and taking the result of that, combining it with somewhere else that is like randomly, predictably, but randomly chosen in a way that is unpredictable for the attacker. Sorry, I mean reproducible, not predictable. And then it's hashing one by one each time until it reaches the final point, which is considered the final hash that you would store in your database. So this way, it's really forcing an attacker that doesn't have as much RAM as you to be recalculating it a lot. It has to recalculate maybe everything, this PBKDF2 at the top every single time, because the attacker doesn't know where you will be jumping from each time. But for us, it's not good because in the web browser, we cannot afford to do hash one by one like that. So let's look at Argon 2, the best practice. Let's see how they do it. So they start by putting 2 columns, basically, that are completely unrelated but created at the same time. So that's the first 2 columns that are kind of the same color each time. And then they start, so the rows are different threads. So it's great in terms of parallel processing. And they take the value from the previous cell on the same row, combined with somewhere not predictable but reproducible, like this C1 R4, column 1, row 4, that gets combined into the result column 3, row 1. And same thing each time to create each of those new cells and try to create maybe even a gigabyte or at least lots of megabytes to outdo the attacker in terms of memory usage towards the right side of the screen, which again means that we have to do all of these hash by hash calls, which we cannot actually afford in the web browser. Like I said, because there's a web worker overhead, so whenever you call the web crypto API, there's actually a starting delay. And if you want to do it one by one, of course, you can do it with JavaScript or WebAssembly, but as we know, it's slow, so it quickly adds up and ends up being a waste of time. So what can we do to go faster? So Argon, as in Argon 1, not Argon 2, originally used AES, even actually the accelerated AES from the Intel CPUs, or what Intel calls AES-NI, and there's an equivalent in the AMD CPUs. But then Argon 2 was released kind of because there were some worries about doing it this way. So they replaced this encryption function AES with a hash, Blake2B, and actually which they even tuned into a smaller, faster function to do all this one-by-one hashing called Blamka. So what else can we do? Maybe we can use some other great R&D from Jean-Philippe Aumasson, again, like his Norks encryption algorithm, which came after the previous password hashing competition. It was released, or at least the latest version was released in 2016. But again, maybe that's something we're not too sure about, or at least I, not being a cryptographer, I guess if they already deemed the first time that it was not a good idea to use AES, maybe Norks, which is much faster than AES, would not be a good idea either. So what else can we do? What can we call from the web browser that can manipulate a lot of data in one go? So there is WebGL, as in OpenGL, but for the web, where maybe we can ask the browser to take this table and do some matrix multiplication or other sorts of 3D processing just to mess with the data enough that it would be annoying to the attacker. We could maybe even use WebCL, as in the compute language, which unfortunately is not getting much adoption. For example, Firefox is preferring WebGL compute shaders instead. But now we are realizing that, well, we are using kind of the same techniques as the attacker in the GPU space, at least. So being in the web browser, there's no way that we can be faster than the attacker with the GPU, because our web GPU kind of technology would be, of course, already slower. So like I hinted at the beginning, maybe we can do password-dependent execution. So you might have noticed when I was talking about Argon 2, there's Argon 2i, as in password-independent memory access patterns. So it means that it's great for a smart card or somewhere where you might be worried about someone doing side channel attacks, like I was showing at the very beginning with lasers or messing with the power, things like that. So it's actually very complicated. And in general, Argon 2D being a password-dependent memory access, you get better security for the same amount of RAM out of it. But if you don't know, if you're not sure which one to choose, basically you have to choose Argon 2 ID, which does half of the execution with password independent and the other half with password dependent or input dependent. So let's kind of take this same distinction, and what if we make this execution in our algorithm that is completely dependent on the input? So that would be really nice to mess with the attackers using a GPU, at least, because they wouldn't be able to do this single instruction, multiple threads. But at the same time, it's the kind of thing we criticize at work, for example, in evaluating security products. It's exactly how a computer or a chip might leak a secret key, because its power consumption, for example, or its interference, whatever signal leakage is leaking, and it's related to the password or the encryption key. So it doesn't sound like a solution either. There's something that we might be able to leverage here that is quite unique to this particular approach, is rate limiting. Because as you remember from those slides with the big blocks and so on, and web technology, web 2.0, 3.0, whatever it is nowadays, you can easily interact with the server from your JavaScript. What if, for example, you do a bit of hashing and you see that you still have time, but before you continue, you want to ask the server to put its little grain of salt into it. So that's what the HMark function would do, for example. Then the client continues with phase 2 up until a certain point, like half a second and 1 second or whatever. And if there is still time, we can ask the server again to put its grain of salt, maybe even more securely with a hardware security module, so that the attacker wouldn't even be able to try to crack the password at high speed or much faster than the actual hardware security module can do, because HSMs are actually usually quite slow unless you buy a really expensive one. So if you're thinking, well, am I wasting your time? I'm kind of agreeing, at least so far, that I've put a ridiculous amount of effort into all of this, and I would really like to be able to go swim and think of actual pebbles instead of cumulative pebbling complexity in designing all these algorithms. So that's why I'm launching a new password hashing competition to find a new standard like the original Argon 2. So the original worked from late 2012, but it's actually started in early 2013, and they elected the winner in 2015. But there are other notable algorithms like YesScript, which you see a lot in cryptocurrencies that originally were using Script. So now they are using YesScript as an easy upgrade path. Lyra2 also is getting a lot of deployment in cryptocurrencies. Catena has actually something that I would really like here, but unfortunately it's not doable in the web client. It's this server relief. And same idea, or even more advanced with Makwa, another notable candidate in the previous PhD, which has this trustless delegation, which means that you can delegate the hard work to even something completely different, like some machine in the cloud or whatever. So you can see all this original data in the original PhD website. And why do I want to do a new one? Well, you can see at PasswordCon 2016, which was mixed with B-sides, Jean-Philippe Aumasson, for example, was asking what's up Argon 2. So asking like, what are the evolutions, looking at improvements since then, because it's ongoing discussion. There's always newer, better and better ideas. And recently, actually, the cat got out of the bag, because I was discussing that with him privately, and with some misunderstanding, he asked about it publicly. So then all of a sudden, everyone agreed that we have to do a new PHC. And so he gives his blessing, even jokingly saying that we should make a blockchain company out of it, but hopefully just jokingly. So seriously, like I said, there's the considerations of Argon 2D versus Argon 2I versus Argon 2ID, and all these new attacks and improvements to Argon 2 itself. So it's not perfect yet, especially in the field of password-independent memory hard functions. It's not a completely solved problem yet. There's lots to do yet. Like I said, there's bandwidth hard functions as a kind of, it's not really completely new, but it's getting attention only now. And other new ideas, maybe like this cache timing safety, and new algorithms that came after the previous PHC. So there was this balloon hashing as a password protection algorithm, which came out after 2015. And this RandomX about the Monero cryptocurrency that seems to have lots of excellent ideas that came out in 2019 or 2018. And finally, this one that is dearest to me, the client-side hashing, especially for web clients, that we need to consider, hopefully. And I would like also to try a different approach this time, as in having a standardized API, making it less academic, like less math formula and more code, especially implementations for Hashcat, John the Ripper, or that sort of thing would be really welcome. Code ideally would speak more than the paper, and the paper itself would be more like a request for comment, actually, and with particular attention to future-proofing, being able to swap out algorithms, things like that. So I've already got several people involved. I'm honored actually to have even Alec Muffet that I mentioned, because his tool, his crack tool that was cracking passwords already 30 years ago when he released it, is on board with this. I haven't had a chance to ask the Loft Heavy Industries yet, but they were speaking at a previous PasswordsCon, so I'm sure they would be interested. There's SciEngines, the makers of those FPGA password crackers that are already on board. As you know, well, I'm part of Team Hashcat. Thankfully, quite a few members are on board. There's TerraHash, the company that Jeremy Gosney founded to sell these password cracking machines, at least based on GPUs. And John the Ripper, also a couple of people have discussed already with. So it's not the very start yet, but I created this website. You can bookmark it or something, and please stay tuned for more soon. Thanks, everyone.